last class we learnt about the digital voltmeter, also popularly known as the dual slope AD converter. The dual slope analog to digital converter we call this as ADC. Is so good. If you buy a digital multimeter today, you can be 100% sure that the heart of that digital multimeter would be a dual slope analog to digital converter, right. Let us recollect what we learnt. The analog part of the ADC is very simple. We have an op amp AC integrator and an op amp comparator. The integrator input is switched to V in or to either plus V reference or minus V reference by two switches. So, we have one single pole double throw switch S1, the second single pole double throw switch decides whether plus VR or minus VR are connected to the integrator, right. So, this is S2. We have the digital system having a counter. We looked at a 3.5 digit ADC. So, I have 3 full digits and the last digit either 0 or 1, and so we have 3.5 digit BCD counter. Then we have the digital logic to control the analog to digital converter. The digital logic has two outputs, switch control 1, switch control 2. The switch control 1 controls switch 1 to either be in position 1 or 2, because it is an SPDT switch. There are two positions for each switch. So, if SC1 is 1, then switch S1 will be in position 1, SC1 is 0, the switch 1 will be in position 2. Similarly for switch 2, right. And the output of the comparator, I call it as Vc. The output of the integrator, we call it as V naught. V naught is nothing but the voltage across the capacitor, because the op amp, if it works properly, whatever is the non inverting input, the same voltage will appear at the inverting input. So, we have already grounded the non inverting input. So, the inverting input also will have the same voltage. So, which means this will be at the ground potential, right. So, we call this as a virtual ground. So, whatever is the terminal voltage at this point of switch S1 will be the voltage across R, because the other terminal is always at ground potential. So, we started looking at the conversion cycle. In the beginning, we assume that the voltage across the capacitor is 0, hence V naught is 0. So, if I look at the starting point, that is the start point, V naught equal to 0. Then we connect switch S1 to position 1. So, let me also put the logic here. So, we have start, we put S1 in position 1 and S2 we do not care, right. We also put for this particular 3.5 digit count equal to 1000, because last class we saw that the final output time T2 would be Vr by T1 into T2, and we said if I make T1 as 1000 counts and Vr as 1000 millivolts, then it becomes a 2 volts full scale voltmeter. So, that is what we are going to discuss again. So, count equal to 1000 and then we start decrementing the count. Count equal to in this case itself decrement count. Then we check count 0, no, we go back and stay in that position, right. So, which means now R is connected to V in, voltage across V R will be V in, current through R would be V in by R. If the voltage is negative, I will have a positive slope. So, this would be V in is equal to negative. If I have the voltage positive, I will have a negative slope. This is V in is positive. Now, if I look at the comparator output voltage, this is Vc, it would be 1, because as soon as V in V naught is become positive, the comparator non inverting terminal is more than the inverting terminal is grounded. So, the output would be 1. So, Vc would become 1, Vc is either 1 or 0, and at the end of T1, which is when count 1000 is over, right, it decrement counts. So, 999, 998, 1000 counts are over. So, T1 itself is equal to 1000 times Tc, where Tc is the clock frequency given to the counter, right. So, at the end of T1, when the count as count down from 1000 to 0, right, the comparator voltage output is checked. So, now we check the comparator. So, if it is V in is negative, we will get the comparator output to be 1, which means V in is negative. So, immediately we can say polarity of input is negative, minus, right. Then we connect S1 to position 2, S2 to position 1, right, and then we keep checking. We also do start counter. So, which means the counter will now is already 0, it will start counting up, right. So, this is count down, this is count up. Then we check whether the comparator output voltage 0, right. If it is no, we continue waiting, the count will keep on counting. When it is yes, we say stop count, output is equal to polarity and count. So, this actually measures T2 with polarity, right. So, we at this point we again start the count equal to 0, and then because the input is negative, I am applying position 2, position 2 is plus VR here. So, earlier I had minus V in plus VR. So, minus V in, whatever current I had flowing through the capacitor, the plus VR will have opposite current, which means the capacitor will be discharged, right. So, at the end we have T2, that would be, let us say n, then count n, right, into clock cycle, right, because when I count 1 on my counter, what does it mean? 1 clock cycle is over. When I count 2, 2 clock cycles are over, right. At the end, of course, we have V in is equal to VR by T1 into n T2. This is what we derived yesterday. This would be 1000 millivolts divided by 1000 counts into n, or this would be cancel out n millivolts, right. Of course, polarity comes from this decision at the end of T1, whether my comparator is going to be 1 or 0 decides the polarity. If the comparator output is 1, polarity is negative. If the comparator output is 0, which means if I look at this particular condition, when V in is positive, my comparator output would be 0, right, up till this point. So, at time T1 the comparator output would be 0. So, what we do is we say, first thing is we take polarity is equal to positive, because I know V in is positive, right. Then we make S1 is in position 2, S2 is in position 2, and start count. Right. Once again we check Vc equal to 0, yes, we continue. If it is 1, then we do the same thing, stop count, output is equal to count polarity plus count, polarity and count, right, not plus, we do not add, we put plus 1, 2, 3, 4 millivolts, right. So, this is the complete logic of the digital circuit to make one conversion, right. So, if we really look at it, at this point in the second stage, this will continue like this, and then at this is, and in the first it will go like this, right. So, this is for V in is equal to negative, and this is for V in is equal to positive. Okay. I am assuming the same voltage for both positive and negative polarity. We did not really look at the output of V naught. V naught would be minus 1 by RC integral V in dt, and then we put this as V in minus V in by RC into T. When can I do that? When can we do that? If and only if Vn is a constant, which means the dual slope digital voltmeter basically measures DC voltage, constant voltage. At least the voltage must be constant between the period 0 and T1. After T1 it can vary, I do not care, right, because I am not looking at V1 Vin after T1, right. So at least for the period T1 we call this as the first integration period, right, and we have the second integration period, that is why it is known as the dual slope. I have one slope of the integrator positive, another slope of the integrator negative, right, and some books call this as integration phase and this as a de-integration phase. There is nothing called de-integration phase, we will simply call it as integration period 1 and integration period 2, right. The so first is that I must have my input voltage constant between 0 and T1, which means it is either DC or at least slow varying AC, where the variation between 0 and T1 is negligible, right. The second thing is, when I start my conversion I need a time period of T1 to do the first integration, a time period of T2 to do the second integration. So the result, my final result, final value n will be displayed only after the period T1 plus T2. So we call this as the conversion time, T conversion is equal to T1 plus T2. For the 3.5 digit multimeter, digital voltmeter, we know we took T1 to be 1000 TC, right, 1000 times the clock frequency, clock time period, right. Then only I will get my n as indicating Vn in terms of millivolts, right, and T2 depends upon Vn. If Vn is equal to 0, T2 would be 0. If Vn is equal to 1 volt, T2 would be 1000, right, because 1000 millivolts, right. So the maximum that the T2 can go is 1999 counts, right, full scale 2000 millivolts or 2 volts. So the maximum that the T2 can occur is 1999 TC, because it has count 1999, then only it can display 1999, right. So the total conversion time, this is maximum, is equal to 2999 into the clock cycle, right. That is a worst case conversion time required before I can take a reading. For most machine applications this is too slow, right, because we know all our computers work very fast, but as long as the meter is going to be for human consumption, I am going to look at the meter and take reading, right. The best I can do is maybe 1 or 2 readings per second, right. So in such a case the speed, the low speed of the analog to digital converter, dual slope analog to digital converter is of no consequence, right. Typically you will get few conversions per second to few tens of conversions per second, that is the best you can get in a dual slope analog to digital converter, but we never use it in that sense. In most of the time we use it as a digital voltmeter, right. So two things, the dual slope DVM is for DC, right, and it should not change with the period T1, okay. And the second thing is the conversion time is quite large. Now let us look at T1. During T1 Vin is integrated, right. Sometimes what happens is you have instruments, you will always get interference and noise on your input, right.
the one interference that we always will get is the power frequency, right, because power frequency, we have power wires running all around our labs, rooms, houses and so on, right, and there would be a 50 hertz or 60 hertz power interference, right. So if I have a 50 hertz or 60 hertz, then instead of having my V in as a constant, I will have a small voltage riding on it, right. If I am measuring volts, this would be very small, we can neglect it, right. Let us say I am going to use this to measure millivolts, the power frequency interference would be appreciable, because that also would be about a millivolt, right. So if I am not using my dVm as a 2 volts full scale, I make it as 200 millivolts full scale, right. I here Vr, we put Vr equal to 1000 millivolts. Now in the second case, I take Vr is equal to 100 millivolts, everything remains the same, but my full scale now will be 200 millivolts, right. So 1000 counts will become 100 millivolts, 2000 counts will become 200 millivolts. So in that case, if I look at the last digit, this is 1 millivolt, the last digit would be 100 microvolts, right. 100 microvolts definitely will be affected by that would be the level of power frequency interference if I simply measure any voltage on any circuit I make in the lab, okay. So is it possible that because I am integrating, I can make this interference go away? It is possible, right, because I know if I integrate a repetitive waveform, right, whose DC value is 0 over one full cycle, then what do I get at the output? 0, right. If for example I take a sine wave, if I integrate for one full cycle a sine wave, I will get 0, because integration gives me the area under the curve. For a sine wave, the positive area and the negative area at the end of one full cycle would cancel, right. So now if I know my interfering signal is power frequency, let us say in India we have 50 hertz, I know power frequency is going to be 50 hertz, and then I make T1 also equal to k times Tf, where Tf is the power frequency time period, in this case 20 millisecond, right. So I make it T1 to not only 1000 times Tc, I also make one more constraint, that it has to be integral multiple of power supply period. In that case, even if I have some small power frequency riding on my DC voltage, that would be integrated out at the end of T1, the effect of power frequency would be 0, right. So if you look at any digital voltmeter, any digital multimeter you buy, the conversion time is always said taking this into consideration, right. Many manufacturers do not know whether you are going to use it in a country like India, where the power frequency is 50 hertz, or you are going to use it in Japan or US, where the power frequency is 60 hertz, but that is no big deal. We can make T1 such that it is equal to K1 times T50, and it is K2 times, that is also equal to KT times T60, right. We take a common multiple such that I will get always integral number of 50 hertz or 60 hertz in T1, right. So if we put these two conditions, then T1 will become, right, for this condition to be met, T1 is 100 milliseconds or a multiple of that. I can have 100 milliseconds, I have 200 milliseconds, right. I can have 300 milliseconds and so on, right, because in 100 millisecond I will have 5 50 cycles and 6 60 cycles, right. So, that would be the minimum time required to reject either 50 hertz or 60 hertz on the dual slope AD converter. Now, there is one more thing that we assumed. I said when we start with the 0 voltage across the capacitor, right. One way of ensuring is put a switch across the capacitor and close the switch, short the capacitor, right, make it 0 and open the switch, right. That is little more tedious, especially when you want to integrate into an integrated IC, right. So, people found another method, right. So, if I am starting somewhere, right, let us say this is my start point, right. So, I do not start here, let me slightly modify this. This is start conversion, right. If I start at an arbitrary point, right, somewhere here I am starting, I do not know what the capacitor voltage, right, but I know the capacitor voltage has to be positive or negative, right. There is only one, its value can be somewhere, I do not know, I do not care what the value is. So, the capacitor voltage is positive, then my comparator output will determine whether the capacitor voltage is positive. If the capacitor voltage is positive or the integrator output is positive, then my comparator will be 1, right. So, now I know my comparator will be 1, okay. So, if the comparator output is 1, I know my this is V naught at start, right, that is V naught at start. So, what I have to do? I have to remove the charge from the capacitor, make it 0. So, to do that I have to connect positive voltage S1 is in position 2, S2 is in position 1, and then I check again for Vc 1, I continue to be in this direction. So, now I have S1 in position 2, S2 is in position 1. So, the voltage is positive here, the current will be in this direction plus VR by R, right, and the capacitor will be discharged, right, capacitor voltage will start reducing. So, I will have a reduction here. At this point, if I look at my comparator voltage, so the Vc will be 1, right, and as soon as my V naught reaches 0, Vc will, this is Vc, will go down, right. So, when Vc becomes 0, I can say go to start conversion, right. On the other hand, when I arbitrarily start at some point, my V naught is negative, this is V naught at start, then my comparator output would be 0, right. So, in that case what we do is Vc is 0, so I connect S1 to position 2 and S2 to position 2, I check for Vc once again,
If it is 0, I continue in this state. If it is crossing to 1, I say start conversion. Right. So, in this case, because minus VR is applied, the capacitor again will be discharged, and at this point the comparator will go to 0 to 1, right. So, every time I use a dual slope digital to converter arbitrarily with a starting point, I must ensure that the capacitor voltage at start equal to 0. To do that, I have to go through this logic. This logic is called auto 0, right. So, this phase is called auto 0 phase, and this phase is called conversion phase, right. So, if you start just like that a dual slope DVM, then we need to go through the auto 0 phase, right. The auto 0 ensures that the capacitor voltage is 0 at the start of conversion, right. So, even though the conversion time is T1 plus T2, if you are doing conversion once in a while, right, you have to go through auto 0. So, the total conversion time is not only 2999 Tc plus I do not know how much time it is going to take Tc for auto 0, right. But the moment I finished one conversion, right, at the end of conversion, what is the output voltage of the integrator? 0, right. At the end of conversion, output of the integrator voltage has to be 0, hence capacitor voltage is 0, I can start the next conversion, right. So, if I do one conversion after the next conversion, we call this as a continuous conversion mode, I need to do auto 0 phase only once, right, at the start. So, I finish one conversion, start another conversion, start another conversion, I continue to do that. If I want to do start stop conversion, I start conversion, stop it, maybe wait for some more time and start again some other time. Every time I do the start stop, I must have an auto 0 phase, right. The very first dual slope analog to digital converter in the integrated circuit form was made by a company called Intercell. They had trouble making, you can Google search and find some history, making the analog part and the digital part in one IC, right. So, they made two different ICs, LD110 and LD111, you will have to combine them on a PC to get a full AD conversion, right, dual slope AD conversion. Later the same company made ICL 7107 and 7106, 7109, right. 7107 is a full dual slope digital voltmeter which will directly drive an LED display, right. So, 7107 is LED display, 7106 is again 3.5 digit digital voltmeter. All these blocks are contained in that single integrated circuit, right, and that has an output which can drive an LCD display, liquid crystal display. The 7109 has no display driver, and it does not have a 3.5 digit BCD counter. The 7109 has a 12-bit binary counter. So, the output is 12-bit binary, right, and later of course you have 4.5, 5.5, right. There is another IC
7135. This is a 4.5 digit DVM. All these two are 3.5 digit, and this is a 12-bit binary output, right. Now, basically the dual slope AD converter is a voltmeter, right. It is a digital voltmeter. We once again take 3.5 digit DVM or 2000 counts full scale. Okay. This is something similar to our PMMC meter. PMMC meter is basically a DC ammeter, right. So, a digital voltmeter is also a DC voltmeter. Let us assume this is plus or minus 200 millivolts full scale, right. To get 200 millivolts full scale on a 3.5 digit DVM, what should be my reference voltage? 100 millivolts, right. So, I give VR equal to 100, I get 200 millivolts full scale. Now, it is very easy, I can put a potential divider, I can put R, put 9R, connect the output of the R to my DVM. So, now if I give V in is equal to 2 volts, then I will get here 200 millivolts, right. So, this is my input, I give V in 2 volts, I get 200 millivolts, which my meter will read as 200 millivolts. Now, if I give 1 volt, I will get 100 millivolts, this will read 100, right, 1000. So, by simply using a potential divider, I can convert the basic 200 millivolts full scale DC digital voltmeter into 2 volts full scale DC digital voltmeter, right. Now, I can continue doing this, instead of 9R I can put 99R. When I have 20 volts as V in, I will have 200 millivolts, because now the division is 1 by 100, right. Okay. So, now my 200 millivolts full scale voltmeter would become 20 volts full scale voltmeter. So, by using a simple digital voltmeter, I can put dividers, right. I can put a divider like this, I can put this R, this is 9R, this is 90R, this is 900R, right. So, this is 200 millivolts and this is 2 volts, 20 volts to 200 volts, and I can also put 9000 R and make it as 2000 volts full scale. Right, but still the DC, it is a DC voltmeter, right, 200 millivolts to. If I want to measure current, right, I have a 200 millivolts full scale digital voltmeter, I want to measure current.
right. What I do is I put 1 ohm resistor and I send a current I. Again this has to be DC because the meter itself is a DC meter, right. So when I is equal to 200 milliampere, then the voltage drop across V1 ohm will be 1 into 200 milliampere, that would be 200 millivolts. So by simply connecting a resistor across the digital voltmeter, right, of value 1 ohm, I have converted the digital voltmeter now to read plus or minus 200 milliampere current. I keep saying plus or minus 200 millivolts, plus or minus 200 milliampere, but all of us do understand, right. You should understand that is it is 199.9 millivolts and 199.9 milliampere. 200, the meter will not show anything, it will overflow. Okay. So simply connecting 1 ohm resistor, I have connected it to 200 millivolts. Now if I connect instead of 1 ohm 0.1 ohm, what will happen? I will get 200 millivolts across 0.1 ohm if and only if I have a current of 2 amperes, right. So instead of 1 ohm, if I connect 0.1 ohm, the same dVm now becomes plus or minus 2 ampere full scale, right. You should understand when I send 2 ampere full scale in 0.4 ohms, right, what is the power dissipated? I square R, I square is 4, R is 0.1, so it is almost 400 milliwatts of power, right. So you cannot extend it saying that okay, I will put a 0.01 ohms and make plus or minus 20 ampere full scale. We can do that, but what is the power dissipation in that 0.01 ohm resistor? 4 watts, right. 4 watts is too much of power, right, it will really heat up the meter. Okay. Generally you will not see this on quite large number of multimeters. Some manufacturers give you, but that meters will be large in size and they have really a big resistor which can dissipate 4 watts, right, in the shunt resistor. So by connecting a potential divider we can convert the basic 200 millivolts or 2 volts full scale digital voltmeter into digital voltmeters of higher value as well as digital ammeter, right. So I can put a 10 ohm here, then what will happen to my full scale current? It will become 20 milliamperes. If I put 100 ohms, it will become 2 milliamperes, right. So I can get 2 milliampere full scale, 20 milliampere full scale, 200 milliampere full scale, 2 ampere full scale, and 20 amperes is little difficult, but we can get. Okay. Now with a basic digital voltmeter we can get DC voltages of any range, DC current of any range, right, and the next one what we would like to measure would be the AC voltages and AC currents, right. So the same thing we can do, we can put a rectifier, full wave bridge rectifier, output we filter and connect the AC input. Okay, we connect AC input, but the moment I put a bridge rectifier, what happens? The diodes will have minimum 0.6 volts to conduct, right. There is a forward drop of the voltage. So I am not going to get 200 millivolts full scale in AC, because 200 millivolts the diode will not conduct, diode does not exist there, right. So if you look at most of the low priced digital multimeters, you will see multiple ranges in DC voltage, multiple ranges in DC current, right, but you will see only 2 or 3 ranges in AC voltage, mostly 20 volts AC, 200 volts AC and
2000 volts AC, right, because less than 20 volts AC the diode drop becomes so big a problem, right. The problem was sorted out by using a circuit called precision rectifier. This is an active circuit, uses op amps. We will look at this circuit in the next class, right. So if precision rectifier is used, then it is possible to get AC currents and AC voltages of millivolts and milliampere range as well. But whether I use a conventional rectifier or precision rectifier, right, the meter will read RMS value only for sine wave, a particular waveform we make it for a sine wave. Later manufacturers, what they did was they used a circuit called AC RMS to DC converters, right. So we have AC voltage input, we convert AC voltage into DC, but the DC is made proportional to RMS. This is another analog circuit which actually does the analog computation. So this V naught of the RMS to DC converter, right. So some digital multimeter manufacturers put this circuit. In such a case they will boldly claim that it is a true RMS meter, their meter is a true RMS meter, because the moment I have an AC RMS to DC converter active circuit, whatever be the AC waveform, I will get the RMS value read by the digital voltmeter. This again we will see in the next class, what is RMS to DC converter. So now using the same digital voltmeter, DC digital voltmeter, we can measure these different levels of DC currents, different levels of DC voltages, different levels of DC AC voltages and different levels of AC currents. Now one thing that the manufacturers added is the ability of a digital voltmeter to measure unknown resistances, right. I have an unknown resistance, I connect a current source, measure the voltage across it, right. Now I make the Is is equal to 1 milliampere, the source current is 1 milliampere DC, right. So if Rx is equal to 1 ohm, what will be the voltage across Rx? 1 millivolts. So if I read 1 millivolt on my 200 millivolts full scale, then I know in this situation Rx is equal to 1 ohm, right. So if 1 millivolt is read, it is 1 ohm. Now if Rx is equal to 100 ohms, what will be the drop across Rx? I am sending 1 milliampere through Rx, 100 ohms, so drop would be 100 millivolts, right. So 100 ohms will give me 100 millivolts if my Rx is 100 ohms, right. This is Rx value, 1 ohm is 1 millivolt, 100 ohms is 100 millivolts, or whatever value is read is actually in ohms, right. If my meter shows 100, it is 100 ohms, right. If my meter shows 1, 2, 3, I know it is 123 ohms, right. By connecting an external DC current source, we can make the same digital voltmeter read resistance as well, right. When a meter reads resistance, it is called an ohm meter, right. So digital ohm meter. So we will stop here, all these additional extensions we will see in the next class.